Yeah.
Okay. Shall I start? Or we need a couple more minutes?
I think we could just start. Yes.
Okay. Hi there. My name is Qiao. I'm a second-year graduate student at the University of Chicago. I am advised by Professor Jacob Bing here. And today I am going to talk about our new paper, Thermal Emission of Terrestrial Planet GJ1132b through the eye of JWST MIRI. So first of all, I would like to talk about how we probe exoplanet atmospheres with the technique of transit. The techniques that I'm going to talk about are called transmission and emission spectroscopy, and I will explain them one by one. I believe that you are all familiar with the term transit. It happens when the planet passes in front of its host star and blocks a small certain fraction of the stellar flux. And we refer that fractional drop in flux as the transit depth. And the key idea behind transmission spectroscopy is that the planet's transit depth is wavelength dependent. So at wavelengths where the atmosphere of the planet is more opaque due to the absorption caused by atoms or molecules in the atmosphere, the planet blocks slightly more stellar flux. To measure these variations in transit depth, the light curves is baked in wavelengths into spectroscopic channels, and the light curve from each channel will be fitted separately with a transit model. And the measured transit depth as a function of wavelengths make up what we call the transmission spectra. So on the right, I showed the transmission spectra of WSP-43b obtained by Hubble Space Telescope, where we can see centered at 1.4 microns, there is a bump, and this is the water feature. The water in the atmospheres of WSP-43b absorbs slightly more light, making the measured transit depth appear to be larger. So basically, if a planet has an atmosphere, then it leaves features on the observed transmission spectra. However, if the planet does not have an atmosphere, or it has a very cloudy or opaque atmosphere, then the measured transmission spectra would be nearly featureless. Similarly, in emission spectroscopy, we observe the light emitted by the planet itself, typically when the planet is hidden behind its host star during the secondary eclipse. During secondary eclipse, the combined light from the star and the planet drops slightly, allowing us to isolate the planet's thermal emission by comparing the total flux before and during the eclipse. So at wavelengths where certain atmospheric gases are present, these molecules absorb or emit radiation differently, also depend on the temperature pressure profile of the atmosphere itself. So that will create specific spectral features. And on the bottom right, I showed emission spectra of the same target, and at 1.4 microns, you can see a dip that is also the water feature seen through emission spectra. Next, I want to talk about our target, GJ1132b. So it is a terrestrial planet orbiting around an M star with an orbital period of 1.6 days. The equilibrium temperature of GJ1132b is around 600 Kelvin, and the bulk density of it is very rocky, about 5.5 grams per centimeter cube. It is one of the best targets to do emission spectroscopy among all of the terrestrial planets, and has an ESM of about 10. So this ESM, the emission spectroscopy metric, it's a quantitative measurement that we use to estimate the observability of an exoplanet thermal emission spectra, particularly in the infrared. And it takes into account the size of the planet, the temperature of the planet, and the size, temperature, and the brightness of the host star. The higher the ESM is, the better the target is suitable for observation. So what's more, M stars, a host star GJ1132 is a M star. They're famous for their activeness and variability, for example, TRAPPIST-1. However, GJ1132 is considered to be a weakly active M-star that has a rotation period larger than 100 days. So the system, the planet itself, and the whole star itself, they're all very good to do emission spectroscopy. And previously, there were two primary transit observations obtained by another JWST instrument, NIRSpec, by May et al. 2023. And on this slide, I showed the transmission spectra from their two visits. But unfortunately, the two visits are inconsistent. The first visit, it prefers a water-dominate atmosphere or a stellar contamination model showed with unaccounted spots. But the second visit prefers a atmosphere-free model. And besides JWST, there were also HIC observations done on this target, and their transmission spectra are also featureless. In terms of thermal emission measurement, Spectrometer has made some effort to look at its secondary eclipse, but because of the instrumental limitation, it results in non-detection. They didn't see any eclipse in their observation. Okay, so since our target temperature is merely about 600 Kelvin, which emits most of the energy as mid-infrared, we use the low resolution spectrometer on the mid-infrared instrument on JWST from 5 to 12 microns to take data. And in this paper, we used the technique, besides the technique of emission spectroscopy, we also use the technique of secondary eclipse thermal emission to probe the presence of an atmosphere. So this technique was originally developed by Code 2019 and Mansfield 2019, and has been applied to some of the JWST observations, such as TRAPPIST-1b, C, LTT-1445AB, and the GI-4A6b. And here I want to explain this idea very briefly. On the slide, you can find the theoretical eclipse depth, which is just the ratio of the emission from the dayside of the planet to the emission from the star, scaled by their sizes. So from this equation, if we have measured eclipse depth, we can invert it to the brightness temperature of planet dayside. And by comparing this dayside temperature to the maximum possible temperature of the planet, which assumes 0 bound albedo and no heat recirculation, we can infer the presence of an atmosphere. And here we define this fancy R as the ratio between the dayside temperature to the maximum possible temperature of the planet. And R is a function of bound albedo and heat recirculation efficiency. So if this R is significantly lower than 1, then it might suggest there is a candidate atmosphere. And in our calculations, we use stellar models from Phoenix to calculate the emission from the star, and we treat the planet as a blackbody. And the emission, they're weighted by photon numbers, since what detector actually sees are the photon counts. We also take into account the instrumental throughput of MIRI, represented by this capital W lambda here. And to minimize the systematics errors, we bring the stellar spectral model to the local resolution of MIRI. Okay, so we have this secondary eclipse depth from our observation. And to precisely determine the dayside temperature of the planet, we need good constraints on A over R star, T star, and RP over RS, especially RP over RS, because any uncertainty on RP over RS goes directly to the measured FP over FS. Luckily, Mahanja 2024 and Eastman 2019 and their package Exofast, they can help us get better constraint on the whole star and planetary parameters. So by using the timing and the duration of primary and secondary eclipses, we can get better constraint on the eccentricity and A over R star of the system. And with this M star K magnitude and the stellar mass relation by Mann et al. 2019, we can determine the stellar mass. And then with the density equation, we can constrain stellar radii. And we do some SAD fitting, we can infer the stellar temperature. So by using this technique and using all of these equations shown on the left, we are able to measure the stellar radius 25% more precise than the previous measurement, and the radius of planet B 3 times more precise, and stellar temperature 2 times more precise. We are also able to measure an eccentricity that is precisely near but not zero. Let's talk about data. So on this slide, you can find the 2D light curve and the 1D light curve of our MIRI observation. We found the observed eclipse depth to be 140 plus minus 17 ppm, corresponding to an 8 sigma detection. And using the technique that I showed in the previous slides, we are able to determine the dayside temperature of 709 plus minus 31 Kelvin, corresponding to a fancy R of 0.95 plus minus 0.04, meaning the dayside temperature is only 1 sigma lower than the temperature for a bare rock. And I also wanted to mention that when inverting the measured eclipse depth to the dayside temperature with this equation, in order to account for the correlation between A over R star, RP over R star, and the T star, which we can kind of see from this SED fitting in the corner plots, in the shapes of the corner plots. We didn't assign an arbitrary Gaussian or uniform priors to do the fitting. Instead, we utilized the MCMC posterior from the ExoFast global fitting to calculate the temperature and the corresponding fancy R. So basically, we took each sample from the posterior from ExoFast MCMC chain, and we took the RP over RS, T effective, and A over RS from that chain. We input them to this equation, and we invert them to get the dayside temperature. We tested 2 different stellar models, Sphinx and Phoenix, to see if they could result in different dayside temperature. The results are shown by the blue and the black lines on this corner plot, but we found the results are basically consistent. And to better understand the results, we also plotted the calculated dayside temperature with our refined host star and planetary parameters with varied bound albedo from 0 to 0.8 and varied heat recirculation efficiency from 0 to 1. On this plot, the red means higher dayside temperature and the blue means cooler dayside temperature. And the contour lines show the median and 1, 2, 3 sigma of our measured dayside temperature. We also placed solar system planets on this plot, but since the solar system planets, they are not tightly locked, we instead use the temperature contrast between their equators and the poles to calculate the heat recirculation efficiency. And from this plot, you can easily find that a Earth-like atmosphere is readily ruled out by over 3 sigma, and our result is 1 sigma consistent with a Mars-like thin atmosphere or a Mercury-like atmosphere-free model. And to place quantitative limits on the thickness of a possible atmosphere, we used this scaling relation for the heat redistribution parameter from Code 2022. And we find an upper limit of 0.7 bars for a pure water atmosphere and a 2.4 bars for a pure carbon dioxide atmosphere. And this helped us rule out the scenario of very thick Venus-like atmosphere. Besides the white light curve analysis, we also want to see if there are molecular features. So here on this slide, I showed the emission spectrum that we took using different data reduction pipelines. And I want to mention that we see very strong nonlinearity in the up the ramp raw data, which is shown on the right. And if to get rid of this nonlinearity, we performed 3 independent analyses with Sparter. It's a Python package developed by the postdoc in our group by removing the first group, by removing 0 group or the first 5 groups or the first 11 groups to see if they cause any difference. And in fact, we found they pretty match each other. They have general same spectral shape, although the one with GR11 has larger error bars. And in the end, we decided to use the one with removing the first 5 groups as our preferred reduction. We compared our emission spectra to a wide range of forward models with different compositions and atmospheric thickness. And here on this slide, I showed the chi-square of different models. We find that actually a broad range of atmospheres are consistent with the data, but the atmospheres that are ruled out readily at more than 3 sigma, they're either too thick, all of these 100 bar atmosphere, and most of the 10 bar atmospheres, or have too much molecular absorptions, such as the pure water or pure carbon dioxide atmospheres. So compared to our previous wildlife analysis, this model with emission spectra allow us to set the upper limit for pure carbon dioxide and water atmospheres at more tenuous surface pressure, because now the shape of the spectra is taken into account. And differing from the wildlife curve analysis, the spectrum now rules out even a Mars-like thin atmosphere, shown with these 2 square orange data points, because Mars has a surface pressure of about 1 millibar if composed entirely of carbon dioxide. And at intermediate surface pressure from 0.1 to 10 bars, the atmosphere models show comparable chi-square values to the best fit blackbody, which are shown with this black dashed line, but do not show an appreciable improvement because blackbody itself can already explain the data well. And similarly, we find that a broad range of bare surface models with different rock composition, they match the data well as well. We also try to determine the dayside temperature using the emission spectra. So you just need to replace the lower and upper boundary of the integral from 5 to 12 microns, which is the broad band wavelength of MIRI, to your specific wavelength bands. But we obviously find that the result from fitting the spectra to our white light curve analysis, they are inconsistent. Well, they're still consistent with 1 sigma, but naively thinking we expect them to be exactly the same. So to investigate the difference, we did a bunch of tests, which are summarized in this table, and we found that the way we treated the uncertainty on each spectroscopic FPFS and the way we treated systematics, for example, including the exponential ramp at the beginning of the light curve or not, it caused the consistency. But since there would always be wavelength-dependent systematics, we could not fully resolve this issue. And in our paper, we ended up presenting the result from the white light curve because we consider it to be the most robust and with less wavelength-dependent issues. And in the end, I also want to discuss JJ1132b in the context of the cosmic shoreline theory. So this cosmic shoreline theory suggests that a planet's ability to maintain an atmosphere is based on its predicted escape velocity and its cumulative extreme UV irradiation. So the figure on the slide shows the cosmic shoreline for a number of solar system bodies and some rocky M-dwarf planets. And the normalized cumulative extreme UV irradiation is estimated using an analytical scaling. This dashed line is a power law from that scaling fitted to match Mars. So the actual EUV irradiation history of individual planet is hard to know. So the blue region shows an illustrative factor of 4 uncertainty. So we actually don't know where is the cosmic shoreline. Maybe it's for sigma away, but we want to prove if this theory is valid. However, our target is placed more than 1 sigma above the shoreline, and farther away from the shoreline are these 3 M-dwarf planets likely to have no atmosphere based on previous Spitzer observation and JWST observations, and recent JWST MIRI observations on TRAPPIST-1b and C also suggest that neither of them has a significant atmosphere. The relative position of our target, GJ1132b, and these other 5 planets again reinforces that GJ1132b is most likely to be a bare rock with no or very thin atmosphere. So the takeaway from this paper is that first we by combining primary transits and secondary eclipse, we measure more precise host star and planet parameters. With our single secondary eclipse observation with MIRI, we're able to measure dayside temperature and the FNCR, which is just 1 sigma below the maximum possible dayside temperature of a bare rock. We obtained an emission spectra. It is consistent with a featureless blackbody that agrees with a wide range of possible surface compositions, and by comparing a broad range of atmospheric models to the dayside to the emission spectra, we ruled out Earth thickness atmospheres, and the atmospheres contain a lot of observers. And based on these results from the wildlife analysis, from the previous transmission spectra, and from our emission spectra, we conclude that GJ1132b likely does not have a significant atmosphere. And this finding supports the theory of a universal cosmic shoreline, because GJ1132b should have received a high level of bolometric and EUV radiation. Okay, I think this would be the end of my presentation, and I am happy to take any questions.
Hi, thanks for the talk. So I wanted to ask, do the stellar models that you're considering, how do they take into account contamination from stellar spots or faculae? Or would that affect your results a lot if, depending on what you assume about the spots or faculae?
Yes. So we do not take stellar contamination into consideration because we are doing emission spectroscopy. But in this May et al. 2023, because they're probing with transmission spectroscopy, they did a range of different stellar contamination models, like uncoated spots, uncoated spots, water contamination, and they found that the first visit can also be explained by a stellar contamination model, while the second visit cannot be. But because if we're measuring the emission from the planet, we do not really care how the star behaves. That's why we don't usually take into account the stellar variation in emission spectroscopy. Does that answer your question?
Yeah, thank you.
No problem. I guess another way to look at it would be, so if the star itself is fast rotator, then yes, the spots also rotate very fast. It will affect our measured secondary eclipse, because when you subtract the stellar flux from the measured total flux, including the star and the planet itself, it will cause difference. But JJ1132b, as I mentioned, it's a weakly active M star. It has a very slow, it's a very slow rotator, and our secondary eclipse, the secondary eclipse duration is less than 1 day, and we don't think that would cause a lot of issues here.
Thanks. Yeah. I guess is there any evidence or is there any way to know whether or not the star was a lot more active in its early history, and maybe that could have stripped off any atmosphere that could have been on the planet? Or is there not really a way to quantify that?
Yes. So when we try to discuss if a M star, I don't know about the other category of stars, but for M stars, we usually look at three parameters. One is the rotation velocity, the rotation period, and one is the age of the star, and the other one would be the log RHK, which is a parameter that can be obtained with the Maclaurin effect by radial velocity, that tells you that also basically tells you how fast the star rotates. Yeah, and I guess that's a really good question. I'm not sure if there are any parameters that can tell you the history of activeness of a star. But yeah, that's a very, very good question.
Thanks.
On your WASP, the original JWST slide that we were just discussing before this, that had 2 different visits.
Yep.
So you mentioned that they're inconsistent with each other. I can see that on the data points, but are the same models on both? Like, what feature are we looking for exactly? It's not clear to me.
Yes. So I think in the first, so first of all, they all look like featureless to me. But what the model suggests that is different between the first visit and the second visit is that you can kind of see a downward slope here at the beginning of visit 1, below 3.5 microns. And this actually corresponds to the water feature. The water feature, it spreads from 2 microns to 4 microns. So I guess this is why the first visit actually prefer a water-dominated atmosphere, while the second one, you can really see a slope here. That's why it prefers a atmosphere free model.
The water models on both, are those curves identical? They look identical to me just by eye, or are those different models? I just can't tell the difference.
That is a good question. I think they're identical. I think they combined the two visits and did the model together. And these are the model, like the color lines, they are the models from the combined analysis of both of the visits.
Okay.
Yes.
And then on the same sort of feature, the 3 to 3.5 micron, it's a lot of like up and down going on there. Is that spectrally resolved on JWST? Like what's our resolving power over there for features?
Are you talking about like this?
Just before that,
Wiggles
like
here?
at the 3.2 micron mark.
Oh, here?
Yeah.
Like this increasement?
Yeah.
So I guess because you cannot see a consistent behavior of an increasement and then a decreasing. So I wouldn't say this is a feature. It might be just a systematic errors from the detector. And the resolution of JWST near spec, I believe it is about 1,000. These are after bending the light curve to different wavelength bands. The raw resolution would be higher than this, and yeah,
Okay.
it
Yeah,
would be
that makes more sense. Yeah.
a lot denser. Yeah,
Okay, thank you.
no problem.
We go to page 13.
13, okay.
Yeah, I'm not quite understand what you are doing here. What's the menu? Group 5 or 11?
Yes, so actually I have a backup slide here to explain the up the ramp data collection strategy of JWST. So HICE also has this collection strategy. So basically the detectors on JWST, it collect photons, actually electrons over time, and each CCD pixel, the bucket, it accumulates charges as electron hit the pixel. But instead of just reading the signal at the beginning and at the end of each exposure, JWST actually continuously samples each pixel multiple times throughout the whole exposure. So this creates a series of samples, or the term that they use in JWST is groups. And as more photons are collected, the charge in each pixel bucket increases over time, and that creates a ramp of signal accumulation. So for a well-behaved pixel, this increase should be linear, meaning the charge, the electrons should be increased at a steady rate as light accumulates. But however, in our data set, in our raw data, the plot that I show on the right, this is the x-axis is the group number. It's like the sample in each exposure, and the y-axis is the data number counts, the electron counts. And we don't see that perfect linearity. Instead, we saw some curve here before in the first 5 groups, in the first 5 samples, and JWST data has shown this. And usually if we have enough groups, we just throw away the last group. So we're kind of worried about how would this nonlinearity affect our results. So we did 3 different data reduction with throwing 0 groups or the first 5 groups or the first 11 groups. And they are indicated by different colors on this spectra.
Insane data volume budget.
Uh,
Sorry, what?
Oh, I just mentioned your sort of data budget on the downlink must have been insane with like 20 groups for on your spec feed. On the proposal,
On
the more groups you have, just your data budget goes really high.
yes,
That's
that's
like
right.
a lot of data to retain and transmit.
Yeah, but I guess so this is really weird because I didn't see this nonlinearity in other MIRI dataset that I have handled. So I guess this is just for this target specifically, or maybe there are other people encounter the same issue already, but they didn't put that in their paper. Yeah.
Most of my science, I don't have to retain the groups, so we just take integration. So I've never had to deal with this.
Yeah.
I mean,
I guess so.
it does make me wonder how much more life those MIRI detectors still have in them. I mean, I guess you weren't taking any data beyond 20 microns, but I know even beyond 15 or 18 microns or so, like the quantum efficiency has just really tanked.
Yeah, the latest throughput curves are like,
yeah,
no, they're pretty bad.
yeah. I mean, it's
Oh no.
yeah, it's always going to be better on that end anyway, but it's still a bit sad how quickly they've gone back.
Was not expecting that part to be a problem on MIRI, honestly. Was expecting the propellant to run out before the detectors went bad.
Is it getting worse with time?
Yeah, I mean it's really affecting
The last
yeah,
channels for sure.
yeah, beyond 15 microns or so, it's really bad now.
Yeah. It's still our only capability, so
yeah.
Well, I was hoping that we can use another 10 years of MIRI, but I guess
get your
some issues
proposals
there.
in sooner rather than later.
Yeah, I mean I guess if
Oh,
you're
that's
sticking,
true.
yeah, if you're sticking with the channels 1 and 2, they aren't as strongly affected by it.
Yeah.
So unless you're trying to look for things beyond, I think pretty much beyond 18 or 20 microns really
Yeah.
is where it's pretty poor.
I think this wavelength range, if this is the data you want, you're gonna be fine from the looks of things right now. It's channels 3 and 4. Or I don't know what they name it exactly. My
Yeah,
naming
channels
is
3 and
whatever
4,
those last
yeah.
two are, yeah. It's a short, medium, long, 1, 2, 3, 4.
Yeah.
Yeah, but 3 and 4.
Okay. I will be cautious of that in the next cycle.
But thank you for the really nice talk.
Thank you for coming.
That sounds good for the job.
Okay. Is that it? Okay.
Yeah.
Thank you for coming.
Thank you.
Yeah, thank you.